Hi everyone, welcome back. So let's try some group problems out. So grab a buddy, grab a sibling, grab a parent, grab a traveling gnome, whatever you need, and get ready to do this. So what we have is a 300 kilogram bar, and it's originally at rest, and it's towed over a series of small rollers. Now those are going to be helpful. They're going to reduce the friction down to what we're going to say is 0. Now that motor M is drawing in the cable at a rate of V equals 0.4 t squared meter per second. We want to know the force in the cable and the distance s it's traveled when t is equal to 5 seconds. So here is your plan. Since we have both forces and velocity involved, we're going to need our kinematics and our equations of motion. So draw your free body diagram and your kinetic diagrams. Then apply the equation of motions to calculate the acceleration, and then use your kinematic equations to determine the distance. So I'm going to give you a few minutes to try this out on your own, and once you have, come on back and we'll see how you did. So 3, 2, 1. Using the magic of technology, you have paused time for long enough for you to attempt the problem, and now you're back. So let's look at this together. Okay, first thing, as always, a free body and kinetic diagram. We know it's accelerating to the right. We also know there's a tension pulling on it, a normal force pushing up, and a weight pushing down. And we're just assuming that friction is 0 because it's on rollers. It's pretty close. It's going to be negligible. Now we're going to apply our scalar equations of motion in the x direction. So we know our tension is going to be equal to 300 times the acceleration, 300 being the mass in kilograms. Now we don't know what the acceleration is yet. However, we know what the velocity is as a function of time. And so if we take our time derivative to get the acceleration is 0.8 t. We can then, if we want to, plug this into our tension equation. And so we have 300 times 0.8 t is going to be equal to that 240 t. And then the tension would therefore be 1200 newtons when t is equal to 5 seconds. Okay, so we have an acceleration now. We have an equation for it. We also have a time. So I think we can go ahead and start pulling out our kinematics. So let's look at this right here. Now we know our velocity is 0.4 t squared. We want to know how far it has gone. We also know that if we have our initial position, we can take the integral of velocity with respect to time to get our final position. Or if we wanted to, we could just say the change in displacement if we wanted to. Lots of ways we can do it. So we plug this in, knowing that it starts at 0, and we have this equation. And then our position will be simply 0.4 over 3 t cubed. We plug in 5 seconds, well that's 16.7 meters it's traveled. So that is everything. Now one question you might be asking yourself is, what about our this equation, plus v naught t plus 1/2 act squared. Why do we use that? We didn't use that because the acceleration wasn't constant. Be very careful about that. You can't use these equations unless your acceleration is constant. Otherwise, you have to come back to our integral or derivative equations. So, thanks for listening, and I'll see you all next time. Bye-bye.